Welcome to the 5th lecture of graph theory. In the last class, we talked about a necessary and sufficient condition for the existence of a perfect matching in a general graph, not bipartite graph. So, this condition was the Tutte's condition, which was expressed like this: Q of G minus S has to be less than equal to cardinality of S for all subset of V of G, right? Because if this was greater, Q of G was greater than S, then there will be, this is the number of odd components, there will be at least one odd components in which one of the vertices will not get a partner from S. So, therefore, we will not have a perfect matching, and the other way was more serious, or it required a more sophisticated proof, that is to prove if there is no perfect matching in the graph, then there is always a bad set. That means there is a set S which violates this condition. That means there is a set S such that Q of G minus S is greater than S. This proof we did in the last class. So, the major steps were to consider a graph G without a perfect matching. Then our intention was to show that there is a perfect matching in it. Instead of showing it directly, we first considered its considered a supergraph G dash of G, and this G dash was called edge maximal supergraph of G with respect to the property of not having a perfect matching. In other words, we added edges into G until it became edge maximal, and then we argued that if you show a bad set in G dash, that is enough. The same bad set will be a bad set in G. That was the first observation. Then after that, we observed that a bad set, instead of looking for a bad set in G dash, the edge maximal supergraph of G, we can as well look for a special kind of set which was like this, some S, such that when you consider the components of G minus S, they are all complete graphs. They are all complete graphs, and the connection between S and each component is complete, like this, and more than that, within S also it is complete. If you can find out this kind of a set S, that will be a bad set. This was the second argument. Then after that, we only had to search for such a set in the edge maximal graph G dash. So, what did we do? We did the most natural thing, namely we collected all the universal vertices, that means the vertices which are adjacent to all other vertices in G, and called it S. So, naturally this S was then a complete graph, because all the vertices inside that are universal vertices, and then if you take any component, the connection between a component and this thing is complete, because they are the things in S are now all universal vertices. That means they have to connect to everybody else. In particular, they should connect all the vertices here, all the vertices here, all the vertices here, all the vertices here, right. The only thing we had to verify was that if you consider any two vertices inside a component, say some x and y, then there will be an edge between them. So, we proved it by contradiction. That means, we assume that suppose there exists two vertices x and y within a component such that there is no edge between them, and then we came up with a contradiction by showing that in that case I can show a perfect matching. In this is an edge maximal graph without a perfect matching. Then if we show that there is a perfect matching in it, it will be a contradiction. How did we show that? So, the first we somehow we proved that it is possible to get two pairs of non-adjacent vertices if there is one pair of non-adjacent vertices in the component, in a component, right. This was x y we selected. Then we can also find another pair u v in the graph, not necessarily in the component now, such that they are also non-adjacent. Not only that, this u is connected to x as well as y in the graph. This kind of a structure is we can get. This is what we showed, right. So, this was showed because this x y is there. So, we considered the shortest path between x and y in this component. In this component, we consider the shortest. There should be a path from x to y because this is a connected component, and then if there is a path, there is always a shortest path. The good thing about shortest path is that there are no edges of this sort or this sort or this sort. This kind of edges will not be there, because then it won't be a shortest path. You can always travel like this, right. So, this would be a shorter path. So, therefore, that edges are not present. So, therefore, you can say if you take x as this and y as this. So, though initially this were the two, this thing I renamed this as y. So, x as this and y as this, and then it is very clear that they are going to be non-adjacent. This edge is not present, and again the other non-adjacent pair u v was constructed by considering this as u. The good thing of considering this as u is that there is these two edges connecting this u to this x and u to y as we wanted here, right. So, and the final thing was just to get that vertex v which is not adjacent to u. How was this guaranteed? Because u is in this somewhere here in this component, right, and therefore, it is not in S, that is u is not a universal vertex. That means, if u was a universal vertex, then it would have been selected to be added in S. We collected all the universal vertices and put in S. Therefore, any vertex you are getting from a component will not be a universal vertex. If it is not a universal vertex, there should be another vertex in the graph to which it is not connected. Let us call it as V. So, that is u v, isn't it? So, now this structure, these four vertices together has this desired structure. So, u is connected to both x and y. This x y is non-adjacent, u v is non-adjacent. Now, look, so the idea was to consider the perfect matching that the near perfect matching, say the almost perfect matching which just misses x and y. That means, so it was presented like if you add this edge to the graph. So, for instance, if you add this edge to the graph, you will get a green matching of G with exactly n by 2 minus 1 edges in it, such that x and y are the only unmatched vertices in each. Similarly, if you add this edge, that means uv, then you will get a say blue perfect matching, blue matching with n by 2 minus 1 edges in it, which leaves only u and v unmatched. These two matchings we considered to create an augmenting path. For instance, we got an augmenting path as starting from x and reaching y. So what did we do? We started from x via a blue edge, right? Blue is there, and then we followed a green edge, and then we followed a blue edge. Like that it traveled, and it could only, if it ends in y, it's fine, we already got an augmenting path. If it if it's an augmenting path for the green matching, if it ends in sorry, I just got confused, 1 minute. So we tried to get an augmenting path starting from v instead of and try to augment the path. So I'll go to the next page. I'm repeating. So this is the construction x, y, and u, v. These are the two edges. So because here I consider, say, let's say I consider this, if I put this edge, I will get a red matching with n by 2 edges, n by 2 minus 1 edges, and then if I put this green this edge here, I will be getting a green matching with n by 2 minus 1 edges. So I see that with respect to the red matching, this v and u are the only vertices which are unmatched, but then there is a green edge going out of this. So then we can follow the green red green red like that. So it will keep going, and then where can it end? If it ends in u, well and good, because it will be an augmenting path of the red matching. So this n by 2 will become n by 2 minus 1 will become n by 2, and we will get a perfect matching, which is a contradiction. On the other hand, if you reach y or x, then you can follow this edge and come here, or this edge and come here, depending on whether it reached here or here, and then that will be an augmenting path of the red matching once again. So this will also allow us to augment the n by 2 minus 1 sized red matching to an n by 2 sized red matching. So which will be a perfect matching, and thus a contradiction, because according to our assumption, the edge maximal graph doesn't have a perfect matching. This is the idea. Now to repeat, what we have done is to prove a necessary and sufficient condition for the existence of a perfect matching in a general graph, and but this theorem can be proved in a slightly different way, which will be giving more insight. And to prove that, we will prove the following statement. So we need some definitions. So first consider a graph G. Suppose if you remove a vertex from G, and it so happens that there is a perfect matching in it, and now you can take another vertex from G and remove a vertex from that. Even then, if you get a perfect matching, and for if you remove any vertex from G, if you end up getting a perfect matching, then such a graph G is called a factor critical graph. That means for any vertex V, G minus V should have a perfect matching. Such a graph is called a factor critical graph. It's clear that if the graph is factor critical, then the cardinality of it has to be odd, because you remove a vertex and you get a perfect matching. If there is a perfect matching, it has to be even, because you have removed a vertex already. The original graph has to have a number of vertices odd, right. Now, let us look at some examples of factor critical graphs. So, for instance, if we can consider this one, say this is an odd cycle 1, 2, 3, 4, 5. This is an odd cycle. So, odd cycles are factor critical because you can try removing this vertex, say remove this vertex, what will happen? So, you end up getting this, there is a perfect matching here 1, 2, right. So, odd cycles are factor critical. So, not that I removed one vertex, you should try removing another vertex. For instance, this vertex if you remove, then also there will be a, so I will do with green now. Suppose if I remove this one, then what will happen is there is a perfect matching like this in the remaining graph. So, if you remove any vertex, you see that in the remaining graph there will be a perfect matching. A similar example is a complete graph. For instance, you consider a Kn where n is odd. Now, what will happen? You can remove any vertex from a complete graph, then see any vertex, it does not matter which vertexes, and then the remaining graph has a perfect matching because this n minus 1 now, n minus 1 vertices are there, it is an even number, you can pair up the vertices because it is a complete graph. So, there will be a perfect matching in Kn. So, K n minus 1. So, therefore, Kn is also a factor critical graph, n is odd. So, let us take another example. What about so a path? So, of course, it has to be odd, otherwise there is no point in saying that it is factor critical. So, here is a 7 node path 1, 2, 3, 4, 5, 6, 7 node path. Now, what about this? Is it a factor critical graph? So, for instance, if I remove this vertex, then of course you will get a perfect matching here. Here is a perfect matching. So, is this a factor critical graph? No, because suppose instead of removing this, so instead of removing this, I removed say this vertex. Suppose I removed this vertex. Suppose I removed this vertex. Then what will happen? What I see is this on one side this graph and the other side this graph. So, you do not get, so you can probably match this one. So, then one vertex will not get any partner here. If I match this thing and then this will not get any partner here, you do not see any perfect matching in this graph, right, in these 2, 3 node graphs. So, therefore, this is not a fact. So, you can try any other vertex. For instance, if you had removed this vertex, then also you will not get a perfect matching because this K will not get any partner. So, that way this is an example of a graph which is not factor critical, odd, but number of vertices is odd, but not factor critical. So, this is the definition of the factor critical graphs. Now, let us see. So, the statement says give me any graph G, then I will show you some subset S in it such that the following 2 properties are satisfied. Again, the first condition is somewhat complicated, but the other condition I will explain second condition is much easier to explain. That means, this S will be such that if you remove S from G, the components of G minus S, each component will be factor critical. Naturally, for it to be factor critical, they all have to be odd, right. Each component has to be odd. Not only that, they will be of odd cardinality, but also they will be factor critical. So, but the first property says, so suppose let me explain what the first property says. The first property says, so that I will be able to show a set S such that if you consider this, let this be the components of G minus S. These are the components of G minus S. Now, see, think of a bipartite graph which is obtained by contracting the entire set into one vertex. This contracting this into one vertex, contracting this into one vertex. So you will, what do I mean by contracting it into one vertex? For instance, if you get this kind of a structure, so if this is S, so for instance this component was like this and there was these connections. So what you do is you replace this with just one vertex, say you can replace it with one vertex, and the connection will be like this. So because this is connected to this, so this vertex also will be connected, this is connected to this connected to this. So in general the contraction operation means if you have an edge like this and then these are the neighbors of it. So these are the neighbors of this vertex, these are the neighbors of this vertex, say some common neighbors also. And then if I decide to contract this, then what will happen is I will merge these two vertices into one. That means I will get a new vertex and all these vertices 1, 2, 3. So all these vertices, this total 7 vertices will be its neighbors. So you may say that there are some double edges here because originally this and this both are connected to this vertex, so therefore there should be 2 edges, but then you can always discard it if you are not interested in multi edges. Sometimes when you are interested in multi edges you may have to keep it, but if you are only talking about simple graphs you can. So this is the contraction operation. So when I say you contract so for instance you can always contract a connected induced subgraph into one vertex by one contracting its edges. For instance, you can contract this edge first and then you will together with this new vertex you will contract this, and then together with this newly formed vertex you will contract this. So finally this entire thing will convert to one vertex and all the neighbors it has outside it. That means any vertex outside this induced subgraph with at least one edge going into the induced subgraph will be its neighbors. Multiple edges will be removed if we are not, since we are not interested in multi graphs as of now. So this is the contraction operation, and then now I am coming back to the this thing. So here I am asking you, because these are components and they are connected. If you look at the induced subgraph on these components, you will see a connected graph, and I can contract all the edges here to form one vertex. So I can form, so this is contracted, I keep it here, and then this is contracted into one vertex, I keep it here, this is also contracted, and then this is contracted. And within S there can be some edges. For the time being what I do is I will remove those edges. So that means I will empty those edges and then make it a empty graph, and sorry, empty, within this it will be empty. So here we will have S like this, this is S, this is this, and then now the connection between this and this will be as before, like for instance all the vertices to which this component is connected, we will keep the edges to those corresponding vertices here, and then all the vertices to which this is connected we will keep the connections here. So that way, so we will get a bipartite graph. So what I have done is each component is shrunk into one, contracted into one vertex, and inside us if we had some edges we just discarded them, removed them, and we retained only the connections across. So if some edge is coming from this component to a vertex here, and that edge will be now coming from this contracted vertex into that vertex. So this graph is a bipartite graph. Now when we form this graph from the given original graph and this subset S, then the statement says you will have always a matching of S. That means you will be able to get a matching such that all the vertices of it is matched, something like this. You will be able to find a partner for each vertex of S here. There can be extra vertices on this side, but every vertex on S side will get a partner. such a matching will be available. Again we will look back. So, these are the two conditions. So, give me any graph G, then you can always get some subset S of V of G such that two conditions are satisfied. One is if you create that bipartite graph from by shrinking the or contracting the components of G minus S into one vertex and maybe deleting the edges inside the S, then you will always get a matching of S. That means you will get a matching such that each vertex of S has a partner. There can be extra vertices on the G minus S, the other side, right. And if second condition is if you look at the induced subgraph on each component, it is going to be a factor critical graph. It is going to be a factor critical graph. It goes without saying that the number of vertices in each component now has to be odd. So, earlier we had considered even components also, but now we say that if you consider this special set S, you will always get each component odd and factor critical, right, apart from that matching property. So, such a set exists, and then says not only that it exists. So, the test for with respect to such a set S, testing for the existence of a perfect matching would be straightforward. What will we do? So, we just have to check whether the number of the components of G minus S is equal to the cardinality of S or not. If the number of components of G minus S is equal to the cardinality of S, then there will be a perfect matching. On the other hand, if the number of components of G minus S is not equal to the cardinality of S, then we are not going to have a perfect matching. In other words, the existence of a perfect matching is equivalent to testing whether the cardinality of S is equal to the number of components of G minus S. See, the first thing we should look at is the second part, that means checking for perfect matching is equal to checking whether the cardinality of the number S is equal to the number of components of G minus S is a very easy consequence of the conditions that the set S itself satisfies. For instance, if you had got a set S which satisfies the two conditions listed here, and then it is easy to verify that the second condition is true. For instance, second statement is true, that means about the perfect matching. Why is it so? We know that if there is a matching of S in that bipartite graph, so definitely the cardinality of S has to be less than equal to the number of components, right. So, what we can get from that is the cardinality of S has to be always less than equal to the number of components of G minus S, isn't it? Why? Because we know that in that bipartite graph we form by contracting each component of G minus S into one vertex and taking S on the other side. The S is matchable, that means S gets a partner for each vertex of S get a partner from the other side. So, there should be at least as many vertices as there are in S on the other side, right. So, the number of components of G minus S has to be greater than equal to S. Now, this means if S equal to, it can be either it can be equal to the number of components or it can be strictly less than the number of components, right. So, these are the only conditions if such a set is given, if the set satisfies this property, right. So, these are the only two conditions. Now, says this, if this is true, then there is a perfect matching, If this is not true, then there is no perfect matching, is what it says, right. If this is true, there is no perfect matching. If this is true, this is perfect, there is a perfect matching. So, that if this is true, that there is a perfect matching is easy to see, because suppose if S is this and the number of components are equal to the cardinality of S, what we can do is we know that also S, you get a matching of S like this somehow. Every vertex of S get a partner on this side. So, there will be one vertex to which it is connected here. So, that is why you are getting a partner, right. So, what I do is I take these matching edges first, this matching edges, and then so once I remove this vertex from the component, because it is factor critical, you will be able to get a perfect matching inside this component. Similarly, here also once I remove this thing, because this component itself is factor critical, you will get a perfect matching here, right. You will get a perfect matching here like this. So, together you can match every vertex. So, this there is nothing inside it, no, every vertex got partners from outside. So, that together it gives me a perfect matching. So, there exists a PM. See, not this was possible because we had the number of components was exactly equal to S. Suppose there was one more component, then what will happen? There is an odd component here which does not get a partner here, because all the vertices of S is finished, because one gone to this, one given to this, one given to this, one given to this. Now, there is one here which is not matchable to S. So, it has to get its partner within this, but then this is an odd component, it cannot be perfectly matched. So, even if you after managing to get the biggest matching here, you will still have one vertex left, it will will not have a partner. So, therefore, you will not have a perfect matching. So, you can see that if it so happens that the number of components is strictly greater than the cardinality of S, you cannot have a perfect matching. So, if you on the other hand, if you have the cardinality of S equal to the number of components, as you see, you can get a perfect matching. So, therefore, that is a very simple consequence of the structure of that set S. If you can get a set S like that in any graph G, then this statement will be true. That means, the cardinality of S equal to the number of components will be the condition for the existence of a perfect matching. So, now the only thing we have to really prove is that such a set exists. But before considering the proof, let us see why this proves the Tutte's theorem again. Because, so this looks like another condition for the existence of perfect matching. That means, it seems to say that there exists some kind of a set, okay, and then you take that set, you just consider the cardinality of it and compare it with the number of components in the corresponding G minus S. So, if they are equal, then there is a perfect matching, otherwise there is no perfect matching. Why is it equal to saying that there is always a perfect matching if there is no bad set in a graph? That was what we did in the last class, right? That was what Tutte's theorem said. So, for instance, if there is a bad set, then there is no perfect matching, is a trivial thing. So, we do not need any proof for that. So, we needed the proof for the other side. That means, if there is no perfect matching, there is a bad set. So, now we claim that the bad set is this set S. So, if this set which satisfy these two conditions will be very much suitable to be taken as a bad set. Why? Because you know that because if there is no perfect matching in the graph, then the cardinality of this set S has to be less than the number of components, and as we know, each component with respect to this set S is an odd component. It is factor critical itself, but it is an odd component. Therefore, the number of odd component is strictly greater than the cardinality of S. Therefore, it is a bad set. So, from the statement here, that means if such a set S exists satisfying these two conditions, then we can infer that the Tutte's theorem is true. That means, if there is no perfect matching, then we should be able to get a bad set, and that bad set happens to be this particular set. So, this seems to be a stronger statement. So, in other words, in the Tutte's theorem, we just told that if there is no perfect matching, there is a bad set. Now, we are saying what kind of a set it is, or in other words, we are giving more information about the structure of that set. how do we yeah. So, now information such right now sorry. So, now we want to prove this statement. So, the how do we prove that such a bad set exists? To prove this thing, so we do the following thing. We first consider this difference. For instance, you can take any set S. Let's take some set S. Now, let us say D of S is equal to Q of G minus S minus cardinality of S. This is essentially the excess. So, in case there is no perfect matching, we know that Q of G minus S for some set Q of G minus S is going to be greater than S. So, there may be some positive excess here, but it can be negative. For instance, Q of G minus S may be less than the cardinality of S. It can be 0, they can be equal, right, if they are equal. So, we define for any S a parameter called D of S, which is essentially the number of odd components of G minus S minus cardinality of S. So, now we collect, let F be the set such that D of S is maximum possible. What do I mean by that? So, for each S you get a value of D of S, and you can see which S has the biggest D of S, but then it need not be a unique set. There can be several sets with the maximum possible value of D of S. Among all the sets, so let us say we collect those sets in F, right, that set is called, the set of sets is called F. Now, among all the sets in F, you can pick up the biggest set in S, set in F. So, this also need not be a unique set, but we can so we can take one biggest set from F. First, F is the set of S's as subsets of E of G such that D of S is maximum, and then we picked up one particular set such that its cardinality is maximum among the sets in F, not among all the possible sets. In that case, I will be seeking the entire set V of G, not that. So, among the sets which have come in F, I will pick up the biggest set. So, let us call this. So, this will be called S from any now on, because this I am going to prove that this particular set is the kind of thing I am looking for. This will have the special structure I am looking for. That means the two properties will be satisfied by this set, right. This is what I am going to do, right. So, so I will for recalling purposes, this set S has this property. So, D of S is greater than or equal to D of S dash for any S. So, for if you consider any other S dash, D of S is going to be greater than or equal to S dash. This is one property, right, for all not equal to S. Now, this is one property, and also among all the sets which have the same D of S, this will be of the highest cardinality. That means we have S is greater, the cardinality of S is greater than or equal to cardinality of S for all S dash with the D of S dash equal to D of S. This is the two properties we have for this S. So, we will come back to this later. So, we will try to use that the set S is the kind of ones we wanted, looking at these properties, trying to contradict these two properties. Now, what I am going to do is, suppose, so I consider this set S, and then I consider the components which it gives. Suppose these are the components. The first thing, because what I want to show is that each of these component is factor critical to begin with, then I will show the matching property. Two properties I have to show. So, how do I show that this is factor critical? So, before showing that it is factor critical, let me show that the component cardinality, the number of vertices in the component is odd. That means, what if it is even, right? So, for that let's pick up one vertex. So, let's mark a vertex here, right. Now, consider moving this to here, it is possible, right. So, let me call it X. So, in other words, I am asking you to consider the set X union X. Then the question is, of course, S union X is a bigger set. So, is it possible that when I remove S union X from the graph instead of S, the number of odd components in the resulting graph is more than the number of odd components, number of odd components in the resulting graph is more than the number of odd components in this graph. For instance, if it increases by 1, what will happen? So, that is exactly what we are going to tell. So, I am interested in this parameter, what is Q of G minus S, say minus X. So, what is S and X m? So, or otherwise I can write it as X union X is removed from S, right. So, let me call it, so for convenience I can call this ES dash equal to S union X. So, now I am interested in this parameter T of S dash. So, G minus S dash minus cardinality of S dash. This is what I am interested in. So, the question is, can D of S dash be greater than or equal to D of S? Can it be bigger or equal? So, if it is bigger, then we already have a contradiction, because in that case S would not have been in F, right. We would not have called D of S as the maximum possible D of S. So, S will not be a set with the maximum value of D of S. So, on the other hand, so which means that the only possibility is D of S dash, and the only possibility is D of S dash equal to D of S, because if D of S is greater, okay, if D of S is greater, then what will happen is the number of we have selected S to F thinking that S is such that D of S is maximum. Now, you are saying that D of S is greater than D of S, that is not possible. So, you can have this or less than equal to this, that is possible. Of course, these are the only two possibilities, right. Now, what will happen if D of S dash is equal to D of S? That is also not okay, because S dash is a bigger set than S, then I would have selected S dash instead of S. Remember from F, the among the sets with the value of D of S maximum, I have picked up the biggest set. So, I would have, but then S dash is a bigger set than S. So, this would be a contradiction to our selection. So, this is also not possible. So, we need D of S dash to be strictly less than D of S, that is the only possibility, right. So, we cannot have this thing because S dash is a bigger set than D of S and S, and then also this strictly greater is also not possible because in that case S would not be in F at all, right. So, now let us see. So, if D of S dash is less than D of S, then I claim that, so that component has to be odd, as we saw this earlier. So, here we considered selecting some vertex x and removing it to S, right. So, if this is an even component, then what will happen when I move an x from this thing. So, here this total will become odd, this will become odd when I cut this. So, it is possible that when I remove this vertex x from here, this may cut into several pieces, right. So, for instance, it may happen that so you took S union x here. So, when I move, so all the other components will remain same, but this particular component from which x was taken, so may cut into, say it may cut into several pieces, but then together the number is odd. If several, this is n1, this is n2, this n3, etc., if all of them add together to an odd number, there should be at least one odd number in it, right. So, there is at least one odd component in the piece among these new components formed. So, this new component is formed because we removed x from this thing. If this big component got cut into several, got divided into several new components, at least one of them has to be odd because the total has to be odd. So, therefore, what we can say is, so instead of, initially there was an even component here, either it got converted to one odd component or it got split into several components, out of which one is odd. So, one more odd component got created. So, we can clearly say that Q of G minus S dash is greater than or equal to Q of G minus S plus 1. This much I can say, right. One more it created. So, what about Q of G minus S dash minus cardinality of S dash? So, that is essentially greater than or equal to G of, that is greater than or equal to Q of G minus S plus 1, because this part is bigger than this, minus S plus 1. This is exactly S plus 1, right, because you have added one more vertex this thing. This is Q of G minus S minus cardinality of S, this is D of S. So, what we get is Q of this happens to be D of S dash. What we get is D of S dash is greater than or equal to D of S. So, in both cases we have seen contradiction. It cannot be strictly greater, because in that case S will not be in F at all, that will be a contradiction because we selected S from F, and if they are equal, S dash is a bigger set than S. So, that will be a contradiction to our selection strategy. So, therefore, that is also not possible. Now, the next thing is to consider, this fact that so we have already shown that each component is factor critical, sorry, is odd, is odd, say. Now we will show that each component is factor critical. How do we show that it is factor critical? So, the argument is, suppose it is like this similar argument, suppose it is not factor critical. So, then it means that I can move. So, for instance, this is my component. So, here is my S. So, there are some other components here, I am just discarding them. So, here I am interested in this component. So, for the argument is true for any other component also. So, let us pick up a vertex and move into this, right. So, now this becomes like this. So, here we have this remaining part. So, I move any x, it does not matter. This is S, x is moved into S first. Now, what happens is this particular set S, so sorry, this is not any x. So, if this is not factor critical, there should be some x such that when I remove x from this, so this becomes, that means this component C minus x becomes a graph without a perfect matching. There is no perfect matching in it, right, in this graph. So, we have to select that x in such a way that this becomes a graph, the remaining becomes a graph without a perfect matching. So, you remove x and move it to S. Now, because there is no perfect matching in it, I know that by Tutte's theorem, that means I am not because I know that this condition is by induction. For instance, for any smaller graph I can assume that the induction is true. That means I can assume that in any smaller graph your theorem is true. So, therefore, I will say this graph the Tutte's theorem is valid. Tutte's theorem is valid means there is no perfect matching, then there is a bad set. I can find a bad set in this graph. So, I should have told about the induction first, because we are proving it using an induction. That means, first we will prove, then we have to check it for trivial cases, like when the number of vertices in the graph is just 0. That is easy, because you can just take phi as a set. If the set S, what will happen is it has only 0 cardinality. So, so you can, there is nothing to prove here, and then so for a vertex 1, that is, so for a single vertex graph also it is very easy to see. You can take phi, because so it is this the one component and they are all that one component, so one component and just one vertex, it is definitely factor critical, because if you remove that, then there is an empty graph. Therefore, it is a factor critical graph, and then trivially you can say that empty set is matchable to this one vertex. So, therefore, for small cases it is easy to verify. Therefore, I assume that all smaller graphs the theorem is true. That means, there exists a subset S with the above properties, right. And then as I already mentioned, if this statement is true by induction, then definitely the Tutte's theorem is also true. That means, there is a bad set if there is no perfect matching in the graph. So, this is a smaller graph. Why is this a smaller graph? So, what if all these things are empty? That means, there is nothing here, even this is empty. So, even then this x is there, that is x, single one vertex is moved to this. So, therefore, this is a smaller graph. Therefore, I can apply induction on that, and there is a bad set here. This is the bad set. This is the bad set. So, bad set I will say. Now, let me call this S dash. So, what is the situation? For instance, I will draw that this is S dash. This component alone I am drawing. This is S dash, and then there are several components here. So, this is the situation. Now, see, remember, this is the full component we saw, this x. So, we had original S here, x was moved from here to here. So, this you remember, because originally this is an odd number as we already shown, then when I moved x, this became an even number, even number in total, right. So the because this is a bad set, I know that S dash cardinality has to be, the cardinality of S dash has to be strictly less than q of this, say this graph is called g dash minus S dash, but can it be just one more? So if it is just one more, then the parity of this term and this term is different. That means if it is odd, this has to be even, if this is even, this has to be odd, if it is just one more. But that is not possible, because if we consider the total number, so if this is odd and the number of odd components is even, the total number of vertices here will be even, because all the even components will contribute an even number. The odd components will pair up, and if there are even number of odd components, they will totally contribute an even number, and even number added with an odd number will give you only an odd number, but we know that total is even, so that will be a contradiction. Similarly, if this was an odd number, this S dash was an odd number, then the number of odd components has to be even, because if the number of odd components is odd, then the total here will be an odd number, and then odd plus odd will be an even number. So that is a problem. So therefore we know the what I mean is, yeah, so the parity of S dash and q of g dash has to be different. If this is S dash is odd, then this has to be even, if S dash is even, then this has to be odd, which essentially means that q of g minus S dash cannot be just one more than S dash, so it has to be at least two more there. We get this q of g dash minus S dash, this is plus 2, right, 2 more we should get. So this is crucial, because what we are going to do is to consider moving the x. So this was the original S, now I move x to it and also S dash to it. So that means x is moved and also S dash is moved. So that means I will consider S union x union S dash as the new set, let it be T. Now I want to analyze the number of components with respect to T. So this will be done in the next class, the proof we will finish in the next class.